This is Mrs. Often, and I'm here today with a short video about perpendicular lines and proof. Before we get started, let's review the definition of the perpendicular bisector of a segment, and we'll use that to define the distance from a point to a line. So you'll remember that the perpendicular bisector of a segment is a line perpendicular to the segment at the segment's midpoint. So if I have my segment AB, and my midpoint is M, then we know AM is congruent to BM, and the perpendicular line is a segment, line, or ray that intersects, making a 90-degree angle with segment AB at point M. The shortest segment from a point to a line is perpendicular to the line. So this is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. And this can be from any point not on the line to a point that is on the line where that segment is intersecting the drawn line at a 90-degree angle. So here we have this diagram. Triangle ABC is shown here. We're looking for the shortest segment from point A to BC. Well, to do that, we would construct a perpendicular. We can see that this segment AP must be the shortest segment because it is making the perpendicular to line BC. So we're going to write and solve an inequality for that, showing that AP is the shortest segment, and therefore AP 12 must be less than AC x minus 8. Or AC is greater than AP, x minus 8 is greater than 12, and thus x must be greater than 20. So any value greater than 20 is going to make this work. A few theorems. If two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So the key here is that it is a linear pair. Form two lines that add, or two angles that add up to 180 and are adjacent, and that those angles must be congruent. So obviously they would both be right angles, and therefore by the definition of right angle, the lines would be perpendicular. Another helpful theorem here is the converse of our theorem about if there's one right angle, then there's 8 right angles. In a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. And we can see that this is very quick to prove. We can prove this using PCA. So these, if lines N and P are parallel, this is a right angle. This angle here must also be a right angle, and therefore Q is also perpendicular to P. Now, if we think about this backwards, if two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. And we can see that this must happen because we have T perpendicular to S, T perpendicular to R. We have a pair of corresponding angles here. They are congruent, and so by CAP, R must be parallel to S. And one additional theorem on parallel lines: if two lines are parallel to the same line, then they are parallel to each other. This is similar to the transitive property. Lines A, B, and C, such that A is parallel to B, B is parallel to C, then A is parallel to C. If we sketch a quick two-dimensional version of this, I have A, B, and C. B, there's C. See if A is parallel to B. If B is parallel to C, then C would also have one arrowhead on it before A is parallel to C. Okay, so let's look at a two-column proof for this. We're given R is parallel to S. Angle 1 is congruent to angle 2. We need to prove that R is perpendicular to T. So what would this look like? We start with what we're given. We notice that because the lines are parallel by PCA, 2 must be congruent to 3. By the transitive property of congruence, 1 must be congruent to 3. And then because 1 and 3 are a linear pair, we're going to point out that it's a congruent linear pair, and therefore the lines must be perpendicular. A two-column proof for this diagram, we have angle EHF right here is congruent to HFG right here. FG is perpendicular to GH, right angle right here, and we need to prove that EH and GH are perpendicular, with this being a right angle right here at point H. So I just want to begin, before I do any proof, by thinking, okay, I've got these two lines, EH and FG. I notice I have a transversal here, so I am going to be using AIP, showing that these lines are parallel to each other. And then I'm going to rely on the fact that I have this right angle here. GH is perpendicular to FG. It is therefore perpendicular to the line to which FG is parallel. So let's see this in action. Starting with our given statements. Then we have EH is parallel to FG by AIP. FG is perpendicular to GH, bringing in that other given. And EH is perpendicular to GH. What you might want to do at this point is try writing this as a paragraph proof, writing the statements out as sentences rather than just a statement reason proof. Okay, so with this given, example 4, we have 1 is congruent to 2, P is perpendicular to Q. We need to prove that P is perpendicular to R. So we start with our given. Notice again that we're going to show that Q must be parallel to R, and that's by the congruent corresponding angles, because 1 and 2 are congruent. Then we are given that P is perpendicular to Q, and then we have the perpendicular transversal theorem here, showing that P is also perpendicular to R. Before you go, be sure that you can list all of the ways that you can use to prove that two lines are parallel. You should have a whole bunch by this time. Thanks so much. I hope you found this video helpful. Have a great one.